Hi everyone, thank you for joining. I'm Shubham. Today I want to talk about how, given a single RGB image, can we reconstruct in 3D the objects and the entire scene that are visible in that image. Of course, given that all of us are here, we probably know and like 3D representations, but I still want to begin with motivating why we want to be able to infer 3D representations given sort of a single 2D RGB image, such as this one here. And to put these 3D representations in context, let's first view what kind of representations have we as a vision community collectively learned to sort of develop. So given this image, I can upload it to Google Cloud's computer vision API system, and it very quickly and accurately tells me that there's an image of a living room, there are some furniture items present, and it can even name some of the items that are present in this image. The state-of-the-art systems we have can actually go a step further and can even label all of the pixels as belonging to some of specific objects and sort of identify what those objects are. Now, all of these approaches are just labeling the entire image or these pixels, and so they're just trying to understand this 2D representation that they're seeing. What they sort of forget is that this image that is shown here is in fact just sort of a window to the world behind it, this underlying physical 3D world behind this image, that in some sense there's this agent or a robot as shown here, it is observing this underlying physical world through just a single perspective. But in some sense, this agent doesn't really care about this image. All it cares about is acting in this underlying physical real world because, for example, if it has to go and sit on the chair, it needs to understand where it can walk, whether the chair is wide enough for it to sit down, and so on. And for these sort of actions, it really needs an actionable physical spatial representation of the world that underlies this image. So while these previous approaches that I mentioned have made a lot of progress in labeling the pixels or labeling the image, they're just understanding this 2D representation for its own sake and not really understanding the underlying physical reality behind this image. And so what I want to talk about today is how we can go from just purely 2D understanding to develop a 3D understanding given a single RGB image, that is, sort of given this image that we saw, how can we develop representations or develop methods that can understand the underlying spatial structure. And at a high level, the approach that I want to talk about is very simple. It just has two components. So given this image, if we want to be able to infer the 3D structure of what we see, we should just take a two-step approach. That is, first, we should try to infer the 3D structure for all the objects that are visible in this image. And once we have that understanding, we can then compose a 3D scene in terms of all these objects whose 3D structure we have inferred, and additionally the surfaces that are present, for example, the walls, the floor on top of the table is there, etc. So what that might look like is we would infer the 3D structure of the chair and all the other objects like the couch, the pillows, the other chairs and the table, etc. and compose a representation where we understand that these two pillows are actually on the couch or the cup is actually on a plate, which is in turn on the table, which in turn is on the floor and so on. And so today I want to talk about two projects that tackle each of these different directions. That is, how can we learn to infer the 3D structure of all the objects? And once we have such an understanding, how do we then build a compositional 3D scene representation? And sort of going into this goal of trying to infer the 3D for all objects, here is just an illustration of what we are after. So given an input image, our goal is to be able to predict the shape, the corresponding camera pose, and maybe even the texture of the object that we are seeing here. And here's just the prediction that the approach I'm going to talk about can give us, that given this image, it infers a reasonable coarse shape of the tiger, also infers its pose as well as the texture overlaid. And we want to be able to do this on other categories as well, such as some others shown here. But remember that the goal was to be able to infer the 3D for all the objects in the scene. And there are just many possible object categories that are out there in the world. Sort of in particular, some estimates are that for some definition of an object category, we have about 10,000 or so object categories that exist in the world. And so we want to be able to develop approaches that can handle these diverse set of object categories, that can scale up to these many thousands of object categories. So there are some characteristics that an approach that wants to be able to infer the 3D of all objects must have. Concretely, so the two characteristics that I think we should care about are the scalability of the approach. That is, if we want an approach for 3D inference to work on a new category, such as let's say we want to be able to infer the 3D structure of okapis, then the amount of annotation or the amount of human intervention required to learn 3D inference for this new category should be as minimal as possible. And so this can really allow us to scale our approach to these tens of thousands of object categories that I was talking about. And the second characteristic is that the approach should be general, as in it should be able to capture the diverse shapes that exist in the world or even within a category. For example, there are many kinds of chairs that exist, and the approach for 3D inference that we develop should be able to handle this shape variation, should be generally applicable across many categories. And so with these two desirable characteristics in mind, let's just go over how is it that we have been tackling object-centric 3D inference actually across the decades in computer vision. And in fact, the task of inferring 3D from a single image is perhaps one of the earliest ones in the vision literature. In fact, it was tackled in the very first computer vision thesis written by Larry Roberts at MIT, where the goal was that given the image on the left, we want to be able to infer a 3D structure as shown on the right, which is understanding this image in terms of this 3D pyramid as well as the 3D cuboid. Though in this case, it was more akin to a 3D detection approach as opposed to a reconstruction approach, because we a priori knew that there are these possible templates of a pyramid or a cuboid that exist, and the goal was just to find them in this image. And over the next few years, this approach was applied to slightly more general scenarios with slightly more complicated templates and arrangements, and even resulted in some impressive demos such as the one you see on the right, where a robot is able to replicate a mirrored version of the configuration it's seeing on the left. And then over the next few years, we followed a very similar 3D detection approach, but generalized it to even more complex shapes such as the razor, that given this 3D model, we can find its instantiations in this image despite significant occlusions, or could even apply it to things like IKEA furniture, where given that we know we are searching for this particular table, we are able to find it in this image. But all of these approaches are essentially trying to find an a priori known object. And so while they're very scalable in that they don't require a lot of supervision to be used for a new object, they're not very general because they don't capture shape variation. For instance, we already know that this particular table is what we are looking for. Given a new table, which is a bit different from this particular table, let's say a curved one, this approach will not be able to this approach will not be applicable towards this slightly different shape. And with the aim of addressing this limitation, we have seen a few learning-based approaches come up over the last few years, which predict a volumetric or a point cloud or a surface-based representation given a single image. And these approaches give very impressive looking reconstructions across many different categories. And the way all of these approaches have been trained is, given an input image, we have some prediction network that infers the underlying 3D structure, and we supervise it using the ground truth 3D that we have available. And while this has led to predictions that work across many different categories, this approach is not very scalable because we require this ground truth 3D supervision during training. And this is extremely difficult to acquire. In fact, I'd argue this is why all of these approaches that you see above have actually only been trained on synthetic data such as ShapeNet, and it's extremely difficult to train these approaches using real-world data where it's very difficult to collect ground truth 3D supervision. And so with the aim of scaling it more or having these learning-based approaches be more scalable, we have seen some efforts towards relaxing the supervision. That is, instead of using ground truth 3D, we have seen some efforts to instead use multi-view images as supervisory signals. So for example, given one image of a chair, we can predict the 3D structure, and as supervision, we can say that this predicted 3D should be consistent with some novel view image of the same instance. And so this relaxes the 3D supervision to requiring only multi-view data. But I'd argue that this is still not very scalable given the kind of data sets that the vision community has collected. In particular, data sets which give multiple views of the same instance are still pretty rare. And for example, if we want this approach to work on categories like okapis or birds, it's extremely difficult to be able to find such multi-view data sets. And so towards really developing an approach that is scalable, we wanted to look at using an even simpler form of data. That is, instead of multi-view collections, we wanted to look at using only single view image collections. That is, we have many images of different birds, but only a single viewpoint per instance. And in addition, we can assume that we have some amount of annotation for each instance. For example, for this bird, we assume that we have an approximate foreground segmentation mask that is available as well. And so we want to look at whether we can learn from this sort of data, as it would be a much more scalable way of learning, as these single view image collections are far more easy to collect across many object categories. So concretely, given an input image, we again want to be able to infer the underlying 3D. But the question is, given these kind of image collections, what is the supervisory signal? Where does the supervisory signal come from? And one possible approach is to enforce geometric self-consistency. That is, we can say whatever 3D we predict should be consistent with the original input, should explain the original input image. And while that's a useful signal, it's unfortunately insufficient by itself. And to best illustrate this, perhaps this example from Edelson and Sinha can be used, where we're seeing the projection of some 3D structure onto the XY plane, but this 3D structure can be something like a cuboid, or it can be something that's far more arbitrary. And in fact, there are infinite possible solutions to what can generate this particular reprojection that we see on the XY plane. And so just enforcing self-consistency will not help us distinguish between these many infinite possible solutions. So while this is a useful cue, enforcing self-consistency is not sufficient by itself, and we need some additional source of signal. And in this work, what we enforce is some notion of category level parsimony. That is, shapes across birds don't vary arbitrarily. If we leverage the notion that across all instances in a category, there's some low dimensional shape space or some shape space that controls the variation of shape across the instances, then by enforcing parsimony in this shape space, we can distinguish amongst the many possible infinite solutions and get to sort of the correct solutions. And we had a recent work that operationalized these ideas, and a lot of it was done in collaboration with Nilesh, who sort of did a lot of the hard work here. Where given an input image, we again have a CNN which predicts sort of an implicit representation of the underlying 3D mesh. And as mentioned earlier, the form of supervision we use are just these single view image collections. That is, for each input image, we have an approximate foreground mask, but importantly, and unlike several prior approaches, we don't use any key points or pose or multi-view data as supervisory signal. In addition, though, what we use is a single template shape per category. So for birds, we have this single template shape available, or for a different category such as horses, we again have a single template shape available that additionally guides learning. And before going into the approach, I want to just clarify what I mean by this implicit mesh as opposed to an explicit mesh. So an explicit mesh representation starts with a fixed mesh, such as this sphere shown here, and it parameterizes any mesh as a deformation of all of the vertices in the original mesh. So if I can pick up any vertex, have a corresponding 3D coordinate, this induces a corresponding explicit mesh representation, where we now have different vertex locations for each of the vertices in the sphere with the same fixed topology. In contrast, an implicit mesh representation is a function that maps an initial source topology, again a sphere, to a different deformed mesh. So this is actually a function that maps any arbitrary point on the surface of the original mesh, such as the sphere, to a corresponding point on a deformed mesh, such as the bear again shown here. But it's a much more continuous and smooth representation because of inductive biases in the function phi, as opposed to an explicit mesh representation where the locations of these vertices are essentially independent parameters. So we want to be able to apply this representation to predict the 3D structure of different instances in a category, and we want to be able to handle different shapes, such as the two horses shown here, where one may have a slightly taller neck or a taller head compared to the other one. Now, to generalize this idea of implicit meshes at a category level, what one might do is learn a separate implicit function for each instance in a category. But this doesn't share the structure, this doesn't enforce category level parsimony, and it does not share any structure across different instances if you're simply learning a separate implicit representation for instances in a category. What we instead do, motivated by this previous work which examined similar ideas in a supervised setting, is formulate a latent variable conditioned implicit function. So there's this common function phi across the category, which conditioned on a latent variable z that determines the instance-specific shape, maps the sphere to different corresponding shapes of the two horses that are shown here, for example. And we further factorize this implicit function into an instance-agnostic mean shape and only an instance-dependent deformation, where this mean shape is actually initialized via the template that I described earlier. And this factorization that the shape of a specific instance is only an instance-specific deformation from the mean shape actually helps us enforce category-level parsimony, where we can say that the deltas that are predicted per instance should not be large, for example. And given this sort of an implicit representation, we can make predictions for the 3D shape for a given instance in a category. So given an input image such as the bird shown here, we have a CNN that predicts the corresponding camera pose, as well as this shape parameter z, which as described earlier instantiates the corresponding shape. For example, we have this template shape, which gets deformed based on the predicted shape variable z, and then based on the predicted camera pi, it can be projected onto the image coordinates, and we get this predicted mesh that is now in the image coordinates. And as a learning objective, what we can enforce is that this predicted mesh should be consistent with the available approximate foreground mask, that the projection of this 3D mesh should match the foreground mask annotations that we have available. In addition, one additional source of supervision that we use are these auxiliary per pixel UV coordinates. So for each pixel, we predict what point on the sphere do we expect to project back on this pixel. Because this prediction is made using only local image evidence, for example, if we are predicting this coordinate for a pixel around the bird's eye, it will only use some very local texture. It enforces that these predictions are actually semantically consistent across different instances in a category. And then we enforce that the spherical point that we predicted actually projects back onto the corresponding location. Sort of more concretely, if we consider this particular pixel for which we have predicted a specific spherical coordinate and thereby a specific point on the template mesh, we can deform this point on the template mesh and project it back onto the image and say that the initial and final locations of this particular pixel should be the same. And so this was an idea we explored in a prior work, and I would encourage you to see that for more details. But essentially, this provides us a way of enforcing semantic consistency across our inferences, and it essentially helps us bypass the need of ground truth keypoint as supervisory signal. So just using a combination of these two terms, enforcing consistency with the foreground mask and cycle consistency with these per pixel mappings, we're able to learn both shape and camera pose prediction using only image collections with approximate foreground mask as supervision. And we also augment this variable z to not just reason about the shape, but also reason about the texture that gets overlaid at each point in the sphere, and just modify the objective a bit to also enforce consistency with the foreground colors that are observed. And essentially, this approach allows us to predict both the shape and the texture on the mesh, as well as the camera pose. And at the end of the day, what we can do is, given a single image of a new bird that we have not seen before, we can use our network to infer the corresponding shape and also the texture that gets overlaid on it. And here we visualize it from some other perspectives as well to see that both the texture and the shape that we infer are actually quite meaningful. And this works across other categories as well and can even handle articulation such as the head of the horse here is bending down. And as I mentioned, our approach only requires very limited amount of supervision per category for training because it only requires approximate foreground segmentation mask. It's easily applicable and scalable to many object categories. And in fact, in the paper, we show results on about 30 object categories. And here are just some sample visualizations across several different animals or other rigid categories such as planes. And I'll actually skip a lot of the details of evaluation for time's sake. But suffice it to say that our predictions allow us to compute correspondences between two different instances. And we use this in some way to evaluate the accuracy of our approach, but I'll maybe skip the details here. And here are just some more results showing on the left the input image. The second column is a predicted shape, then with overlaid texture, and then from a novel viewpoint. And we again see that we can predict meaningful 3D across many object categories, and the coarse shape is pretty accurate. We can predict certain forms of articulation, such as the head of the donkey at the top bending down, and the texture that we predict is also actually quite accurate. And maybe here are just some more results from 360-degree views showing the reconstructions across some different categories. And we see that the approach actually works on a wide variety of categories. For example, the shapes of airplanes or birds or hippos are actually quite different from each other. But for each of these categories, our approach is able to capture the underlying 3D structure. So what I talked about so far was focused on inferring the 3D structure for all the objects in a scene. But this was inferring the 3D structure at an individual level or separately for all the objects. And what we want to now look at is, suppose we do have an understanding of the 3D structure of each of these objects in isolation, how can we better compose a consistent and coherent 3D scene from this? And so just to sort of put the previous approaches in perspective, the central question is, given our ability to represent each object in isolation, how is it that an agent should represent the entire scene that it sees? And the previous approach that I mentioned essentially amounted to identifying each separate object and predicting some representation, such as the shape representation for each of them in isolation. But unfortunately, this approach ignores the relationships amongst these different objects, amongst the different components in the scene. For example, it ignores the fact that there's the cup that is present on the plate, which is on the table. And these relationships are actually crucial for humans to understand any complex scene, and in fact sort of are very interesting. For example, if we see this particular video, the spatial relationship between the objects, the trampoline and the sheep, is actually what's perhaps the most interesting part of it, or how that spatial relationship is changing over time, because the sheep is sort of jumping on the trampoline. And perhaps that's why this little girl is excited, that it's really the new relationship between these objects that is the salient part of this video that I'm showing here. And it's very interesting to be able to understand this sort of relationship. And sort of not just from an interesting perspective, but these relationships are actually fundamental and critical to understand for many tasks. So for example, if a robot has to pick up the plate here, it needs to understand the spatial relationship between the plate and the other cups on top. Or for example, this Jenga playing robot from MIT has to understand the physical relationships between all these objects, or the relationship between the tennis racket and the ball in this scene. So our approach is to not just represent the individual objects or the individual components, but also represent the relationships among them to then compose a coherent 3D scene. So concretely, the goal that we have is, given an input image, we want to be able to predict the underlying 3D structure, which again is in the form of predicting an object-centric 3D representation. That is, our goal is to be able to predict a shape and the pose for each object in the scene, but predict these in a way such that the overall configuration is coherent. And as I mentioned earlier, the prior approaches typically predicted only the scale, translation, rotation, and the shape in an independent manner. That is, they would look at each object, such as the table or the chair, in isolation and predict the shape and pose for each of these objects in isolation without paying any attention to the relationships among them. What our approach does is, in addition to these unary individual predictions, also predicts the inter-object relationships, or more concretely, predicts the relative pose from one object to the other. That is, for this pair, we might predict where is the table, or what is the relative pose of the table with respect to the chair, and sort of also vice versa. And then we combine these unary and binary estimates to better obtain a per object pose and shape prediction that are sort of informed globally by these binary estimates that we also made. And just to go into a bit more detail on each of these, on sort of how we combine, given the unary estimates and the binary estimates, we can obtain updated global estimates by simply sort of a least square optimization. That is, given initial estimates of the unary and relative pose terms, these are essentially just linear equations over the optimal translations for both of these objects, and we can sort of compute the optimal solution by just inverse least squares. And I'll skip some of the details here. But essentially, this can be thought of as an explicit form of message passing, where given these two objects, the message is of the form of the relative pose, and this message updates our estimate of the pose for each of these objects to give us a more refined estimate. And just to show you some examples, this is an approach, factored 3D, which predicts the 3D structure of objects independently. And while the shape and pose is approximately correct, the relationship between them, these two, is sort of quite off because the table is not really in front of the chair. Whereas our approach, which takes the relationships into account, actually refines this. So just to show this again, our approach corrects this estimate to be something like this, which is more coherent with respect to the relationships that we see. And here is just another example where independent prediction doesn't really respect the relationship between this couch and the table, whereas our approach, which takes into account the relationships, does a better job at composing the entire scene together that has a coherent relationship between these two objects. And I'll also again skip over some of the details, but we can also compare to other implicit forms of message passing as opposed to this explicit form of message passing. And sort of the main takeaway is that any form of message passing actually helps, but that the explicit form of message passing that we proposed, that is more relevant to the underlying task of predicting these predicting the absolute poses, is a bit more accurate. And we evaluated this across two different data sets using this AP metric, where sort of higher is better. But I'll skip some of the details again. But just looking back, the overall approach that I showed you was essentially very simple, that to compose a 3D representation of a scene by first understanding all of the objects in isolation and then reasoning about the relationships among them. And what we saw was that we should be able to predict the 3D across many object categories if we learn in this self-supervised manner without requiring ground truth 3D by just enforcing geometric consistency between the image evidence and the predictions that we have, while enforcing some category level parsimony. That this approach can really allow us to scale to many, many object categories. And then subsequently, that it's really important to be able to reason about the relationships between these different objects when we are trying to compose a coherent 3D representation of the entire scene. That it really helps to reason about, let's say, where the table is with respect to the chairs in this image. Yeah, thank you for your attention, and please let me know if you have any questions.